Okay, we'll go ahead and get started. Again, welcome to today's webinar, Blockchain Development Outside of an Audit. My name is Greg Moranci. I'm the Marketing Director with FP Complete. Today we have the pleasure of learning more about blockchain development from Senior Software Engineer Neil Mayhew. Neil is a Senior Software Engineer with FP Complete, specializing in blockchain and Haskell. He's currently leading the team that's implementing a new cryptocurrency for the Genie Foundation. It's geniefoundation.org. He has many years of experience developing software for systems ranging from small embedded units to large fleets of servers. This will be a presentation and a discussion into blockchain development. We will pause and collaborate upon questions presented to us throughout the webinar. If you have a pressing question that you feel you need immediate attention to, you may email us directly at fpcomplete.com/contact us or call 858-333-6397, and we will address your immediate needs. Here is Neil Mayhew.
Well, hi everybody. Glad you can be here. And I'm looking forward to all the things that I can share with you about blockchain and how to be successful at developing with blockchain. We realized from the people who've signed up for this webinar that there's quite a variety of different backgrounds that people are coming with. So one of the things I want to do at the beginning is to make sure that we're all on the same page about the concepts and about the terminology. So here is an outline of what I'm going to be covering today. And the first 4 points are essentially background information to make sure that we all get onto the same page. And then we'll get to some more meaty stuff in the second half. There is a Q&A facility that comes along with the webinar software that we're using, Zoom. So you can actually enter a question at any point if you want to. And I encourage you to do that as we go along. We'll pause after each major section to look at what questions have been asked. But if you can get the questions in early, then we can be thinking about them, and there'll be a longer Q&A section at the end. So we're going to start out now just by talking about what is a blockchain to make sure that we all understand the same thing by that. People use blockchain as a synonym for a lot of different things. Often people use the word blockchain interchangeably with cryptocurrency, but they're not the same thing, and we'll talk about that and the fact that blockchains have a wider application than just cryptocurrencies. So at its very simplest, a blockchain is just a chain of blocks of information. And in this illustration that I've put together here, the gray part of each block is regular information that you may wish to record and store and access. And then the blue section is a reference to the previous block. So each block refers to the previous one, and that goes all the way back to an initial block called the Genesis block. And usually these links are done in some kind of a database with some sort of key reference, but a blockchain can be represented in a lot of different ways. But the point is that you've got information, and each new block of information that gets added to the chain depends on all of the previous blocks right back to the beginning. Other aspects of what a blockchain is. So at its very simplest, it is a chain of blocks of information, but there's a lot more to the concept than that, because such chains of blocks of information have been around for a long time. So one of the characteristics of blockchain that's quite important is that the whole chain is essentially a shorthand for a large body of information. Because each block refers to the previous one, if you have the most recent block, the one that's at the head of the chain, you essentially have all the other blocks as well. And all you need is that one first block. And if you have an accurate copy of that, then you have an accurate copy of everything else. And it has similarities to other computer engineering concepts. So for example, there's something called content addressable storage. And this is a way of just keeping a fingerprint of some large piece of information and being able to retrieve it later. But one of the differences between blockchain and regular content addressable storage is that a blockchain allows you to make incremental changes. you could just add a new block on top, and there may be thousands of blocks in the chain already, and you don't have to disturb any of them. Whereas typically with content addressable storage, if it's a large image that's hundreds of megabytes long, you have to change the whole image and then get a new handle to it. So some examples of things that you might want to have as a large body of information that you would store this way as a blockchain would be some sort of record of events. When new events keep arriving, you want to keep track of previous events, but you want to add a new one on top. So a blockchain is an ideal form of storage for that. And in the cryptocurrency world, the events that you're recording are basically financial transactions. And so then the whole collection of those are what we call a ledger. It's a global, publicly accessible ledger. And it's essentially a record of all the transactions that have ever happened. Another example would be representing some sort of backup of a directory where you would want to refer to not just the files in the directory itself, but there would be subdirectories and subdirectories, and you'd want a single way of referring to the whole thing. And another would be perhaps the state of an entire system or operating system where you want that to be reproducible, and you want basically a handle that refers to a specific generation or version of the system. Another thing about blockchain is that there are many participants. It's not just for internal storage. So the chain is essentially a shared state that can be agreed on by all the participants in the network. And usually there's some sort of consensus protocol built on top that enables all the participants to come to an agreement about what the shared state is. But a blockchain is a really good model for this, because if you're all agreed on the current state of the chain, and then a new block is added, for example, a new transaction in a cryptocurrency, then you don't actually have to rewrite the whole chain because it's incremental. You just have to all agree on, yes, this is the additional new block that we're going to add, and then you're back to having agreement throughout the network. Another thing that blockchain provides is that it's tamper-proof data. You can't go back and subtly change the contents of a block in the middle of the chain, because all the other blocks depend on it. And if you did that, you'd have to change all the blocks that sit on top of it. So this is a great way to have records that once made must never be changed. It avoids you having to go through and check gigabytes of data each time to see if anything has changed. All you need to do is check the head of the chain. The most recent block determines the entire rest of the chain. So all the rest of the chain is then fixed for all time. And that's particularly something you want to have in a cryptocurrency, because you don't want people to be able to withdraw transactions or somebody else to be claimed that they were never paid. One of the characteristics of a blockchain is it makes extensive use of something called public key cryptography, which is a term you may or may not have heard about. If you haven't, it's a pretty neat thing that's been invented over the last couple of decades. What public key cryptography allows you to do is to have a very strong form of verification. Verification that data is correct, and verification that data has originated from a specific place. So usually built into that is the idea of identity. The public key that you use identifies you uniquely. Nobody else can end up clashing with that same public key. So that key becomes a unique part of the identity of who each participant is. However, the other thing that enables is anonymity. Because public key is cryptography is so strong, just the key and nothing else is sufficient to identify someone. Normally in the banking world or the real estate world or whatever, there are various aspects of your personal identity that would need to be checked in order to verify that, for example, you're the owner of a property or that you're the holder of a bank account. Whereas with the public key cryptography, you just need that one key. And as a result, you can be completely anonymous apart from the existence of the key. And this enables private financial dealings, a lot of other things. You don't have to go to some central authority to establish who you are. And the only piece of information that is known about you is that you're the key holder. So strictly speaking, it's actually pseudonymity because you are still identified by the key, but that's the only piece of information that's revealed about you. And that's very important to a lot of people participating in blockchain for one reason or another, and particularly, as you can imagine, in cryptocurrencies. One other thing about blockchain is that it's very socially empowering. So what do I mean by that? Well, one of the things that people value, particularly for cryptocurrencies, is the personal autonomy and privacy that they get. So they get the anonymity or the pseudonymity through the public key, but it also enables everyone to participate in financial transactions on an equal footing, or in the case of other types of blockchain, in other kinds of interactions and participation. And you don't have to have special permission or sign up with anything to get started. And this is a very socially empowering thing for people in society. But there are other ways on a global scale which it's socially empowering as well. So nowadays we have a global economy, and we increasingly engage in trade with people in other countries, especially in developing countries. But it has in the past been very difficult for people in developing countries especially to get involved, because they have to go through so many middlemen in order to sell their goods and services. And very often those middle agencies are corrupt and siphon off a lot of the money and so on. And a blockchain enables these people to be able to participate kind of on their own merits, freestanding, and that's very empowering for them. And another way in which blockchain is socially empowering is it can be a great agent for social justice. So going beyond just currency and the justice issue of people getting cheated or having to pay exorbitant fees in order to engage in international trade, blockchain can be used for some really interesting things, such as proof of land ownership and that kind of thing, and for minority peoples in countries with oppressive regimes. Blockchain can be very helpful for those people to establish their ownership in the first place of a particular piece of land, and then for that ownership to stand for all time. If they were dependent on the government to keep land records, corrupt people in the government can just go and change the records, and the small person has no recourse, no way of ever proving that that got changed. So something like a blockchain can be really important for enforcing human rights. So that's some background just on blockchain itself. Moving along, how do companies make use of blockchain technology? We're assuming that most of you have come from a company here, and you're thinking, how can my company make use of blockchain technology? So what are some of the things that blockchain is actually used for, which I've alluded to already? So obviously cryptocurrencies is a big one, and that's so well known that often when people mean cryptocurrency, they say blockchain, but that's actually inaccurate. Another interesting use of blockchain at the moment is for what are called supply chain guarantees. Every company that sells goods and services, particularly if they do so in the retail market, has a supply chain. They're not the originator usually of the products. And so, for example, Walmart has an awful lot of supply chains that they have to take care of because they have so many different products on their shelves. And one of the problems that they have is being able to identify for an individual item where it was actually sourced. Because, for example, particularly with foodstuffs, if it's discovered that there is some contamination that's happened from a particular supplier, and in Walmart's case a few years ago, it was lettuce, and a particular batch of lettuce was found to have been contaminated with E. coli. But unfortunately, Walmart had no way of tracking which lettuce on the shelves came from which batch. And in the end, they had to throw out all the lettuce on all the shelves in all of their stores, which, as you can imagine, was an extremely costly loss for them. And so a couple of years ago, they decided to start building some technology that would enable them to track this so that they could then just get rid of the particular batch that was contaminated in whichever stores it went to. And so they partnered with IBM, and they now actually have just gone live with using the blockchain to track that. And not just with lettuce, but particularly with prawns. Apparently, A lot of the prawns in the world are actually farmed in India by small rural farmers. And what Walmart want to be able to do is to trace the shipment of these batches of prawns all the way from the original farmers. And IBM has produced a blockchain-based solution for them to do that. Now, in the articles that I read, I wasn't 100% sure why they needed to do it with blockchain rather than something else. But some of the things that I can think of is it would be very easy for, say, a small rural farmer in India to get on board with maybe just a cell phone app to essentially be able to then start creating blocks on the blockchain. So the first block on the chain would be them actually producing a batch of prawns, and then every intermediary that it goes through would add another block to the chain, which they would sign with public key, and so on all the way up to Walmart. And so there's no way for corrupt individuals in the middle of the chain to go changing and hiding the origin of things because it wouldn't check out. So blockchain can be a very good way of tracking that kind of thing. Another use for blockchain that's been suggested, I'm not sure that it's gone live anywhere yet, but this is really interesting, is for medical records. And the idea is that over time, you have a medical history, different diagnoses are built into that history, lab results, all kinds of different things. And the idea is that that would be information that you would own personally, and you would choose who you shared it with. But it would mean that if, for example, you were applying for medical insurance and the insurance company wants to know what your medical history is, because the individual events of your history would be on a blockchain, it would be impossible for you to hide them or lie about them. So that's an interesting possibility that's opening up that people are beginning to look into. But what I should emphasize is that all blockchains are built basically on the same technology. So whether one is for cryptocurrency or for medical records, they are all essentially using the same technology. So those are some uses that not cryptocurrencies, some uses that blockchains are put to, but how might you use them in your individual company? So one of the obvious things is that you could just trade in cryptocurrency. You could accept, let's say, Bitcoin as payment for the services and goods that you offer. But that's not a particularly challenging thing to do. There are lots of guides and examples on the internet of how to do that. So the next thing you might think of doing is to build an application on top of an existing blockchain. So you wouldn't be implementing the blockchain itself, but you would be writing some application that stores information on an existing blockchain or uses it in some way. Again, that's not especially challenging to do because somebody else has implemented the blockchain. There's usually an API for interacting with it. It's all there ready to go, and there's usually information on how to do that. Another thing that is often included in blockchains that I hadn't touched on yet is something called smart contracts, which is where individual blocks on the chain can actually encapsulate a contract, which is usually expressed in some sort of pseudo programming language that's executed by a virtual machine. And when you put that contract onto the blockchain, it can't be removed. And there are usually trigger conditions at which the various liabilities and fulfillments go into action, and that can all be handled automatically as those conditions are met. So that is one thing that companies are starting to use, is smart contracts. But again, that would be specific to each blockchain and is not particularly challenging to do because there's information on how to do it. You may want to just use the blockchain to manage some shared information that you need to share with other people. And again, that can be attached to a chain fairly easily. Where it starts to get a bit more challenging is if you want to represent business processes using your own blockchain. This is where you would be designing a blockchain that is specifically designed to accommodate whatever your business processes are. And you would be thinking about how to transition from whatever existing mechanism you have for running those processes into doing them with a blockchain. So that starts to get more complicated because you are most likely going to have to either adapt an existing blockchain or implement one from scratch. And then the ultimate level of difficulty is implementing your own cryptocurrency. There's a pretty high bar for that. There's a lot of pitfalls, which we'll be talking about later. This is actually something that I'm working on right now, as Greg said in his introduction. I'm leading a project to implement cryptocurrency for the Genie Foundation. And this has some innovative features that are actually pretty interesting, and you can read all about it at the geniefoundation.org. So blockchain is a good thing. There are a lot of cool ways that you can use it, but what are some of the downsides of deciding to use blockchain technology? So one of the most obvious ones is that there is a lack of central control. The basic idea of a blockchain is that it's very democratic. A lot of the responsibility for it is distributed. There isn't usually one central authority controlling it. It is possible to set a blockchain up that way, but generally speaking, if you do, people are not going to think that it's a true blockchain. So what that lack of central control means is that you can't just go changing the rules whenever you feel like it. Once you've established the blockchain and the software that operates it, and different people are participating in it, running that software, you can't easily say, oh, we just want to change the way it operates, change the rules by which it works, because it's out there, it becomes its own entity, it has a life of its own. Another way in which you don't have central control is that if somebody else decides to change the rules, they can do something called forking your blockchain, which means that they modify the software to change the rules, and from a certain point in history onwards, it all starts to operate according to new rules. It's not compatible with your blockchain anymore, so there's a parting of the ways. And if the majority of people want to go with the forked blockchain, there's nothing you can do about that. So it's a bit like forking in an open source project. Another downside is that there is high visibility for the data that's on the blockchain. Basically, everything is in the open. It's designed to work that way. One of the things that's interesting about cryptocurrencies compared with regular banking is that with a cryptocurrency, every transaction and every participant for all time is visible. You can go on the ledger and find out how much is in any given account. The thing is, you don't know who that account belongs to. So it's kind of the opposite of regular banking, where you know who the account belongs to because their name is on the checks, but you have no idea how much the money they have in their account or who they've paid from that account. So it's kind of the backwards thing, but nevertheless, with the blockchain, you need to recognize that all the data is out in the open and you can't take it back again. If you decided to make that data private, if it was just on a server that you controlled, you could simply shut down the server and hope that nobody had siphoned off all the data. But in the case of a blockchain, that content of the chain is replicated to every node on the network, which means that you could never get rid of all of those copies of the data, no matter how much you try to litigate against people. Another thing to remember is that transactions are irreversible. Once a block has been added to the chain, you can't ever remove it. And particularly in the case of a cryptocurrency, this means if you paid someone by mistake, you paid, for example, to the wrong account address, there's no way that transaction can be reversed. If I do that with regular currency, I can contact my bank and say, oops, I made a mistake. Could you please reverse this? Or the person on the other end stole my money and has not provided the service. There are ways of doing that with the regular banking system, but with something blockchain based, once it's done, it's done. You can never get it back. And in the case of a cryptocurrency, the only thing you could do is rely on the goodwill of the person at the other end to send you the same amount of money back again. There are unforeseen uses and abuses of blockchains. Now, we're all familiar with the reputation that cryptocurrencies have for being tools of the dark web and being used for trading in drugs and arms and assassinations and so on. So I don't really need to talk much about that. One thing to be aware of is that thefts and losses are a bit different with a blockchain, particularly a cryptocurrency, where essentially nobody else is responsible for any mistake you made. If you didn't guard your secret key properly and somebody steals it and empties your account, well, that's your problem. Whereas with the bank, if a bank gets robbed and loses a lot of cash, the bank is still liable to give me back my money. But another unforeseen use that you may not have thought of is something that I've called piggybacking, which is where somebody decides to develop an application on top of your blockchain, and it actually ends up becoming a significantly dominant use of the blockchain. So for example, somebody created a game called CryptoKitties on top of the Ethereum blockchain. And this suddenly took off in popularity to the point where a majority of the traffic that was going on the Ethereum network was actually CryptoKitties, people playing the game, which was totally not what Ethereum was designed for. And the developers and administrators had to get together and figure out what they were going to do about this, because it was actually costing all the participants a lot of money, because there was this huge frivolous CryptoKitty traffic going on top of the same blockchain. I'm not sure how that was resolved, but it is something that could happen to any blockchain that you set up. Somebody could start using it for something that you didn't plan, and that starts to become an inconvenience. It's also worth remembering that blockchain is still a very new field, even though Bitcoin itself has been around for a long time, and that was really the first major use of blockchain. We're still learning a lot. The new currencies coming out all the time, and new blockchains coming out all the time, new uses for blockchains. So it is still quite new. So if you're going to get into it, you have to recognize that it can be a bit of a bumpy ride sometimes. So for example, there is a shortage of experienced staff who know blockchain already. It's very easy to make mistakes of one kind or another, because a lot isn't known about the pitfalls, and best practice surrounding the use of blockchain and currencies is constantly changing. You have to keep up with that. Blockchain can have some quite steep hardware requirements. So for example, the blockchain, if it gets large, and typically they do, is replicated to every single node in the network, which often would just be people's regular PCs that they have at home. And in the case of the Bitcoin ledger, for example, it's several hundred gigabytes. And that has to be stored on every single machine that wants to participate in the blockchain. So that's a cost that you have to factor in. There are ways to do things called light nodes, but there are certain provisos to do with that as well. The other thing is that blockchain can often use up a significant amount of CPU time, because there's something called proof of work that I'll be talking about later, that is usually associated with every transaction. And so if you're going to operate the blockchain, you need to make sure that you're going to have enough CPU to do all that number crunching. And then, of course, there's the issue of what I've called optics, which is what does it make you look like as a company if you're using blockchain? A lot of people automatically assume that blockchain is somehow a tool for criminals, so that could make you not look good. Other people see blockchain as just a passing fad, and if they see you doing it, they say, oh, well, you're just trying to look cool, and this is all fluff, don't take you seriously. And another problem is that some people think that blockchain is the answer to everything, and they'll sort of jump on the board and go over the top with it. So you have to steer a middle ground, really. Okay, so then now another of our introductory sections, and I think this is the last of the introductory ones. What does some of the terminology mean? I just want to make sure that we're all on the same page about that, so as we talk about things later, there won't be any misunderstandings. So one of the terms that we throw around pretty freely is hashing. And many of people will be familiar with the idea of a hash table, which we've got in a little illustration on the right-hand side there. It's a way of grouping information into buckets in an efficient way so you can access it quickly. But that's not really what we're talking about with hashing here in the blockchain context. Hashing here functions more like a more powerful checksum. Those of you who've been around in the computer industry for a while may be familiar with the idea of a checksum. A credit card number, for example, the last digit on a credit card number is called a check digit, and it's actually computed from the other digits. If somebody has typed in the number wrong, made a mistake somewhere along the line, the check digit won't agree, and it will be known that there was a mistake and they should retype the number. So we're talking more about that kind of thing. So if you take a hash of a set of data, and then the data gets changed in any way, you know that the hashes won't agree anymore. If you recompute the hash of the data compared with the original, you know that some corruption or meddling has happened. So hashing is extremely useful for verifying things, but the modern hash functions also have a property called collision resistance, which means that no two inputs produce the same output. Now, that's not theoretically true, because obviously a hash is typically going to be some small number of bytes, like 32 bytes, for example, whereas the inputs may be hundreds of megabytes. However, because the modern hashes are quite long in the sense of the number of bytes that they compute, it's the probability of two inputs ever producing the same hash are mind-bogglingly small. So as a result of this, it means that we can actually use a hash as a kind of fingerprint for any data that we want. Even if it's a very large body of data, you take the hash, and then that hash uniquely identifies that data, and it is essentially interchangeable in terms of identifying the data. It's obviously not interchangeable in terms of the original data. You can't get 200 megabytes of information out of 32 bytes, but it is a unique fingerprint that you can apply to any data. And this is an important part of the way blockchain operates, because each previous block in the chain is referred to by its hash. And this is why the chain can't be altered, is because if anybody made any alteration on the chain, the hash of each block would change. And ultimately the hash of the block at the head would change, and that would be detected. Another thing that's important about hashing is that it's irreversible. And this means that you can't recover the original data from the hash. And this is very important for all kinds of privacy. Another thing about hashing is that it's randomly distributed. So because those 32 bytes of the hash look just simply like random numbers, you can't even infer anything about the original data, about its length or how many 0 bytes it contains or anything else. And so this is, again, important for security and privacy. Some of the commonly used hash algorithms that we use today, you'll probably have heard of one called MD5. That's been around for a long time and is now not considered to be best practice. There's the SHA, SHA family. We had SHA-1, and that's been superseded by SHA-2. There are variants of that, such as SHA-256 and SHA-512, which indicate the number of bits in the checksum that they compute. Those are considered best practice nowadays. However, the trouble is they're actually pretty slow to compute. And so there's some new ones that have come along, such as Blake-2, which have a lot of the same robustness as the SHA family, but are very much quicker to compute. So you will find a lot of blockchains are now using Blake-2. Okay, so that's hashing. Another term that you will hear bandied about is Merkle Tree, which sounds really fancy. It's actually not. It's a neat idea, but it's not that hard to understand. It's just a convenient label for a concept that gets reused a lot. What a Merkle tree is a tree of blocks of information, and blocks higher up in the tree record the hash of the blocks lower down, and then the blocks above those contain the hash of those blocks. So you've actually got hashes of hashes of hashes. So if you look in the diagram there, the top block, which has got 3 blue boxes in it, those are 3 hashes of blocks further down. And the block on the far right is gray, which means it's just information, but the 2 blocks on the left at the second level there are themselves lists of hashes, which are the hashes of blocks further down, and so on. And because each level in the tree is hashed from the blocks that are below, the result is that the hash at the top of the tree represents everything in the tree. And if you change anything anywhere in the tree, you change the hash at the top. So this is similar to the idea that I floated earlier about a blockchain, but it expands the idea to, rather than just a chain of blocks, it's actually a tree of blocks. So it's a form of recursive hashing, where things lower down in the tree get hashed, and then the higher up you go, you keep hashing as you go. Some examples of this that you might possibly be familiar with is the Git version control system, which stores files within directories, and then directories within directories as trees of hashes. And then the history within Git is also another Merkle tree, where each commit contains the hash of its predecessor commit. And so if you have the head of a branch, you've got the hash of what's on the head of the branch, it uniquely identifies everything that's gone before on that branch and all of the files that are stored in the repository for each commit. And blockchain itself is a form of Merkle Tree. So I have a diagram here that shows that. This is essentially the same diagram that I had earlier, but I've represented it diagonally to show you that it is essentially a tree that's going on. It's just that at each level in the tree, there's only one branch, but it is still a Merkle tree. So if you hear this term bandied around, it's really just referring to this idea of recursive hashing and having a single hash at the end of it that refers to everything else in the tree lower down. Okay, so I want to say just a little bit more about public key cryptography at this point, because although I touched on it earlier, I didn't talk very much about how it works. So it revolves around the idea of key pairs, and that's why it's called public key cryptography. Because if everything about your key was public, it wouldn't actually be very useful because anybody could use it. So in fact, what you have is a key pair. There's a secret part and a public part. And the public part is something you publish to the world at large, and the secret part is something that you keep very, very private. And they're often called key pairs because sometimes we talk about the public key and the secret key, but they're really just different aspects of the same key. And in fact, usually you can calculate the public key from the secret key if you have it. But we typically talk about them as key pairs because they go together uniquely. And there are various algorithms that are used. Well, actually, there's something else I wanted to say about that. So with public key cryptography, what you do is you publish your public key. And then if somebody wants to send something encrypted to you, they can use your public key to encrypt it. And only you with the secret key can ever decrypt it. But it does mean that you don't have to have any kind of shared secret between you. Anybody who has your public key can send you something privately. They just have to establish whether or not the key really does belong to you. But that's very much easier than having some sort of password that's used for symmetric encryption, where you have to keep that super secret and yet you've had to share it with somebody else. The key pairs can be used the other way around for digital signatures, where somebody can sign something with the secret key and then anybody can verify it with the public key. And so they know that that piece of information is uniquely validated by you, the originator, and not from somebody else pretending to be you. So there are various public key cryptography algorithms that are used, and you may well have heard of something called RSA, which has been around for a long time and was the main encryption that was used in HTTPS. But that's now been superseded by elliptic curve cryptography, which revolves around the same idea, which is a very difficult mathematical puzzle that you can only solve if you have the secret key. But it uses a mathematical concept called elliptic curves rather than using prime numbers like RSA did. So elliptic curve is really where it's at nowadays. It has a number of advantages. It has much shorter key lengths for the same degree of security. Over the years, we've had to keep increasing RSA key lengths, and they're quite long now in order to be secure. Elliptic curve takes us back to smaller keys, and it's generally faster to compute and just better in a lot of different ways. So I've already talked about some of the uses of public key cryptography. So there's encryption, where you want to send information secretly to somebody else. And then there's signing, where you want to be able to verify that this information is correct and came from the requisite individual. And this is a big part of blockchains. Typically, we're not using encryption because the blockchain's intended to be public, but signing is very, very important. So in a cryptocurrency, you need to know that a send transaction really did come from the person that's supposed to be sending the money and not somebody else who's trying to find a way to empty their account. And then it's also used for identity, because if you can sign something, then it identifies who you are. And the public key will be unique to your secret key. And so you can use that as a kind of fingerprint for you, which is effectively a form of identity. Some more technology that I'd just like to cover. I've talked already about consensus. This is a word that is used a lot within the blockchain world. And what it means is a way for all of the participants, all of the nodes on the network, to arrive at a common understanding of what the shared state is, typically of a ledger or a blockchain. And arriving at that is actually pretty complex because all of the nodes are operating asynchronously with network delays and unreliable network connections and a lot of other things like that. So we'll talk a bit more about consensus in a while, but that's a very important concept to be aware of. Mining is another thing that you will hear, and it's often said that mining is what creates new Bitcoins, for example. And most currencies have some sort of similar thing. It's actually not quite true to say that mining is just for the purpose of creating new Bitcoins, as if you could kind of dig them out of the ground or do the digital equivalent to that. What happens with Bitcoin mining is that miners compete to add new blocks to the end of the chain. And what they have to do is to solve a difficult cryptographic puzzle called proof of work, which basically qualifies them to be allowed to add a new block to the chain. That block will then contain some number of transactions, typically 1,000 transactions. Each transaction has a fee associated with it. And the miner who is successful in solving the puzzle first gets to collect all the fees, and that's how they make their money. Now, there is also a mining reward associated with the block as well, but it's usually much smaller than the fees. Proof of work. This is where you have to expend a considerable amount of CPU power and therefore electricity that you're actually paying for with money in order to qualify in some way or to establish that you're bona fide and genuine. So in the case of Bitcoin, for example, the proof of work is costly, which means that the people adding blocks to the chains have a built-in incentive to abide by the rules and not be disruptive and to essentially uphold the rules for everybody else. It's a way of having skin in the game, if you like. The downside to that is it's costing the world an enormous amount of electricity to do this. So an alternative mechanism is called proof of stake, which is where each node gets voting rights proportional to the amount of the currency that they hold, and then consensus is achieved by a majority of votes, but the votes are weighted by the amount of stake that you have. So it's essentially a set of nodes that controls more than 50% of the currency gets to vote on which blocks are accepted next. But you can delegate the voting rights for your stake to a representative node that's sort of higher up in the food chain. So what happens in practice is there's a relatively small number of nodes on the network that control the voting rights for a significant proportion of the overall stake of the currency, and they get to control what happens on the blockchain, but no one of them has actually 50% itself, so there isn't an opportunity for even a corrupt representative to control things, but it does mean that you don't have hundreds of thousands of nodes all having to vote on every single block. So that's proof of stake, where skin in the game is determined by how much stake in the currency you have, or how much people who have a stake in the currency have trusted you to be involved in the consensus. Forking, I already talked about. I would ideally have liked to have an illustration for this, but if you can imagine that at a certain point in the chain's history, if an alternative head block was added, and then blocks are added on top of that, you would end up with a Y-shaped blockchain with two alternative histories going back to a certain common point in the past. So this can be done maliciously to try and subvert the blockchain and steal funds, or it can happen if somebody wants to change the rules, which is the context that I talked about it in before. So forking can happen and can be a way of stealing money and that kind of thing. But that when people say forking, that's what they mean. They're basically producing an alternative version of history from some point on. And one of the reasons for proof of work, for example, is that it would be very expensive to create such an alternative history because you'd have to do all of the mining for all of the alternative blocks in the history. And the idea is to make it so expensive to do that that no one would actually ever have a proper incentive to fork. Okay, so that's all introductory stuff up till now. Now we'll start to get into the meat of it a little bit more. About how we actually go about implementing a blockchain. So I haven't paused for questions at this point at all, but I haven't seen any questions in the Q&A box. So if there is anything you'd like me to pause and talk about right now, now is the time. Otherwise, I'm going to continue going forward. Okay, the things that make a blockchain challenging to implement. So one thing to recognize right at the start is that there are some very high stakes involved. So if you make a mistake, your mistake is likely to be very, very costly. Obviously, in a cryptocurrency, you could see it would be a monetary cost. But in other kinds of blockchain, there would be all sorts of opportunities for corrupt data and for people to manipulate the data if they somehow found a weakness in what you've done. Based on the different examples I've given of what blockchains can be used for, you can probably envisage ways in which that could be costly if somehow somebody was able to subvert your blockchain. Blockchains are highly attractive targets. Even if somebody isn't hoping to make off with a lot of money, they're still, from a kind of hacker point of view, extremely attractive. If a hacker can say, hey, I hacked the such and such blockchain, it's enormous kudos to them. So every kind of small hacker and his dog is interested in hammering away on any new blockchain that comes out, see if they can find what the weaknesses are, see if they can basically screw things up for you. So if you put yourself out there with a blockchain, it becomes a highly attractive target, which means it's really important that you get it right because a lot of people are going to be trying to break it. Another thing to be aware of is that downtime can be costly because where you have a majority of nodes having to vote on things, if somebody can do a denial of service attack on a significant proportion of the nodes on the network, maybe not crashing the machine, but just simply swamping the network connection so that they can't participate in voting, you could actually swing the vote in a direction where it's not supposed to go. These things are called 51% attacks. Now, it can be anywhere between 50 and 100, of course. It doesn't have to be 51, but that's usually how we refer to it. The idea is that if you can somehow either get control of or remove 50% of the network, then you can actually do things that would otherwise be impossible. So even if your software doesn't have any vulnerabilities in it that would actually make it perform incorrectly, if somebody can just take some of your nodes out of service, it does lead to an actual then security risk. Okay, the other thing to realize about blockchain is that cryptography is a really integral part of it. And cryptography is a very, very deep subject. A lot of people think, hey, I've just read the specification for such and such an algorithm. I'm going to write my own implementation. So in a word, don't. The way I phrase this is that friends don't let friends implement their own crypto. It's way more difficult and complex than you might think. And so your friends shouldn't be letting you do it. What you should be doing is using existing crypto implementations from people who have expertise in that field. So basically what you should be doing is using libraries for all of the cryptographic functions that you need to use. And that the great thing is that there are lots of those libraries around. So they shouldn't be hard to find, although they do vary in quality. But even if you are using a library, you still have to know how to use it appropriately. It's very easy to take a really well-written cryptographic function and totally compromise its value by not using it properly. A really dumb example would be, for example, not using a cryptographically secure random number generator, just whatever your language or operating system provides. And if you're not using genuinely random numbers or close to it, then all the hashing and signing in the world is not going to be very, very valuable. So you do need to know how to handle cryptography correctly. And this does make it challenging to implement a blockchain. Another thing is that running a blockchain is essentially a form of real-time software. Now, it's not hard real-time in the sense that, say, an aircraft navigation system would be, an aircraft fly-by-wire system, but nevertheless, there are time constraints on what you're doing, and there's an awful lot of things happening at once that your software has to keep track of. So a blockchain is essentially a peer-to-peer network where you've got a whole lot of nodes around the world all talking to each other and chattering away to each other. So this means that it's event driven, in that you've got network packets coming in from other nodes, potentially hundreds of them per second. And you have to respond to all of these, and you have to respond to them in a timely way. And you can't just simply do things in the order that you would want to. You have to just wait for the events to come in and then respond to them. It's very asynchronous. You've got all of these nodes in different places doing things on their own schedule, and all sorts of things will be overlapping or happening at unpredictable times. You have to be able to accommodate this in the software. Also, your software needs to be autonomous. Although, for example, if you have a cryptocurrency application, there will be a user interface that allows the person to see what's going on in their account and maybe some of what's going on the network. They, most of the time, they'll be sitting there passive. However, the node software has to keep churning away, responding to all of these peer communications that are happening and recording blocks in the ledger that are arriving from elsewhere in the network. And there's no human operator there to intervene if there are problems or restart it if it starts to go wrong. It has to be completely autonomous and be able to operate in the background 100% reliably for long periods of time. The software has to be remain responsive regardless of the constraints that are placed upon it. In particular, you need to recognize that for many blockchain applications, the blockchain software is going to be running in a consumer environment on somebody's PC that they're using for other things, and that is not necessarily a super fast machine with a super fast network connection. But the software has to remain responsive despite that. It's working basically with shared resources. So if somebody decides to play some 3D shooter on their computer at the same time as running the cryptocurrency, then that's inevitably going to have an impact. You can't assume that your software is just going to be able to take 100% of the CPU whenever it wants. There's also shared disk space, shared network bandwidth, all those kind of things. The software has to remain responsive under all of those conditions. Another constrained environment that it might run in would be perhaps IoT. You may actually have IoT devices that are out there in the field needing to do things on the blockchain. So that needs to be able to run both reliably and responsively, despite the fact that you may have a fairly low-powered system. You will also have to face unreliable connectivity. If you're running some sort of node in the cloud, in AWS, for example, you can be fairly sure that you're going to have reliable connectivity, but most of the places this software is going to run, that's not going to be the case. The software has to be high throughput as well. As I was saying, you could be having at times hundreds of transactions or hundreds of network packets a second coming through the system, and it has to be able to handle all of those smoothly and not get bogged down. So there is a need for fairly high performance. Okay, so then the blockchain software basically are highly complex systems. They are highly distributed. So when we talk about distributed systems, we're usually thinking about sort of, a few tens of nodes all communicating with each other. But in something like Bitcoin, for example, you've got hundreds of thousands of nodes active on the network simultaneously, all of which are potentially communicating with each other. These are some of the biggest distributed systems we've ever constructed as human beings. And trying to think through all the implications of such a distributed system and how to code for that is extremely challenging. In addition to being distributed across a lot of different computers, typically the software needs to be highly parallel even within the one machine. You need to have a lot of different threads all taking care of different aspects of the blockchain. And that makes it very difficult to reason about your software when it's in a highly multi-threaded environment. The algorithms themselves are extremely complex, as well as just the systems being complex. It's very easy, for example, to introduce what are called race conditions, which is where you have two threads, for example, trying to perform the same or similar actions at the same time. And if they do them in the wrong order, things can get really messed up. So you need to make sure that your algorithms can't allow for any race conditions to happen. They're basically robust against things happening in parallel. And what also makes the algorithms complex is that there is almost always no absolute measure of time. It's a well-known thing in computer science that if you have a distributed system, it's not possible to have a single clock that everybody agrees on that measures time in exactly the same way. So a lot of people try to solve things like race conditions by saying, oh, well, we'll just timestamp things. But that doesn't work because every node will have a different idea of what the current time is, and you can't rely on that. So the algorithms themselves are complex, difficult to understand, and need a lot of care and thought in developing them. Okay, so let's talk a little bit about consensus. So as I've said before, consensus is a way for the entire network to agree on some shared state. It is an eventual agreement on system state because at any one moment in time, some nodes may have an additional block and some don't. But what you want is for within some reasonable period of time for all of the nodes to be able to settle on what the shared system state is, the state of the ledger, for example, the state of the blockchain. Consensus needs to exist because there's no central authority controlling things. If you think about a bank, the bank keeps the definitive record of everybody's bank account, and it is the ultimate authority on how much money is in each account and who has paid who. But most blockchains don't have any kind of central authority. They're completely autonomous, and things are arrived at simply through consensus by all the nodes agreeing on what needs to happen. But it's very difficult to design for something like that. It's a totally different way of thinking about constructing software when there is no central authority controlling things, nothing that you can fall back on and say, oh, well, we'll just make a decision here and everything else will abide by it. So consensus is a very complex thing. One of the consensus algorithms that's fairly well known is called Raft. But even Raft relies on there being a leader. All the nodes elect a leader, and that leader serves for a certain length of time, but nevertheless, there is a single leader. But typically with blockchain, you can't run it that way. And the other thing is that these consensus algorithms have to be something called Byzantine resistant. So there's a classic computer science problem called the Byzantine generals problem, which is modeled on a group of generals in wartime needing to communicate with each other and close in on a target from different directions. And if a certain number of generals collude with each other and send false information to the others, they can actually subvert the whole operation and seize power. And so the same thing can happen with consensus algorithms. So you need an algorithm that's resistant to some proportion, let's say a third of the nodes actually colluding with each other and being corrupt and attempting to subvert the network. And the consensus needs to be majority driven, but it can be quite difficult to decide on what is the majority, who is the majority, how is all that being decided. But this has to be built into the consensus algorithm because ultimately with a blockchain, that's what drives it, is the majority. And the blockchain needs to be properly incentivized. You remember we talked about the proof of stake and the proof of work. These are ways of providing individual nodes with incentives to abide by the rules. And if you haven't designed your incentivization properly, which is essentially an economic consideration, if there are incentives to break the rules and misbehave, then that's going to happen. What you need to make sure is everybody has an incentive to behave the right way, and that needs to be built into the consensus algorithm. Okay, another thing that makes blockchain complex is platforms and deployment. So typically you will have a mixture of desktop and cloud. because you will be running some cloud nodes, which are sort of the backbone of the network that keep things going regardless of who comes and goes. But often the software will be running on a desktop system as well. And those are quite different environments. But you need to be able to essentially deploy the same software or a build of the same software to those different places. You will inevitably end up dealing with a mixture of releases because it's up to all the individuals on the network when they upgrade their software, and you may well be running the network with the current release, the previous release, and the one release before that, all active simultaneously, and your software has to be able to operate reliably in that situation and not simply assume that everybody will be running the latest software. You will typically be dealing with multiple operating systems too. Yeah, it's pretty much a given that you'll have to release for Windows and also for Mac. But increasingly Linux is important as well, either because the kind of people who are going to want to get involved with your blockchain in the beginning are the kind of people that will be running Linux, or because you'll be running Linux on your cloud nodes. So you will end up building your software for all three platforms most typically. And maybe some other Unix style operating systems as well, such as BSD or AIX. So those are some of the things that make blockchain complex to implement. What are some of the main security issues that you may have to face and think about? Well, there's the operational security side of your network, particularly of your cloud nodes. Now, it turns out that the great majority of cryptocurrency thefts that have happened over the past few years have all been as a result of some kind of social engineering, which means that you didn't actually find a weakness in the software. What you did was you found a weakness in the people. You somehow encouraged them to click on a picture of dancing kitties, or you convinced them that they needed to sign up for something, or something, some way of duping people into acting in a way that then gave away control or secret information. So the great majority of vulnerabilities are actually a result of this. And so that's probably the thing that you need to tackle above all. And in the end, there is no substitute for user education, making sure that users understand what their best practices are and what they should and shouldn't do. But you need to recognize up front, if you're going to operate a blockchain, that is a part of your responsibility right from the beginning, that people that are involved in it in one way or another, either in using it or in controlling it, are properly educated. The second most common vulnerability is actually DevOps weaknesses. So it wasn't actually a weakness in the software itself, it was that some of the servers in the cloud weren't properly secured, or were running outdated versions of software, or not had a patched operating system, that kind of thing. So DevOps is actually a really important part of making sure that blockchain is secure. Key theft is a big deal. If somebody steals someone's private key, they can empty out the account, for example, or put false information on the blockchain, and there's nothing you can do about that. So the key is really, really important that you protect it against theft. But key loss is also a big deal. You may have heard about the Quadriga exchange, or rather the death of the founder of the Quadriga exchange a year or so ago, where he hadn't actually shared some of the secret keys with other people in the company, and he went off to India and died there, and massive amounts of currency were lost simply because the original keys were lost. There is no way to get the key back. So there has to be really careful management around that. And this points to the fact that with blockchains, there are a number of single points of failure that you really have to be careful of and try to avoid. So for example, I talked to you about Genesis blocks. There's a Genesis key that goes with that Genesis block that's used to sign it. So if somebody is able to steal your Genesis key, they've basically got complete control of the entire blockchain because they can re-sign everything from the beginning. Another point of failure, particularly for cryptocurrencies, has been exchanges, where some of the bigger exchanges have actually controlled a very significant proportion of the money in the currency. And then if somehow the exchange itself is compromised, then there's a huge impact on the currency. And I believe When one of the bigger exchanges, Mt. Gox, was compromised, the currency lost like 20% overnight. I mean, it did bounce back, but nevertheless, it was a huge impact. And people, there are always going to be people that have a significant amount of control because people have to hold the keys and various other things. And if you can somehow get at those people, or those people mess up or behave unreliably in one way or another, that is a single point of failure for the whole system. There are, of course, software vulnerabilities. These are actually fairly low down on the scale of things that can go wrong based on previous experience. But if you have somehow got some weakness in your software that people can exploit, they will exploit it. And that may well not be in your application code. That may well be in a library that you depend on, or some other thing associated with the blockchain. Contract languages, for example. I talked about smart contracts before. Some blockchains have been let down by the fact that the code implementing the blockchain was really, really secure, but the contract language was thrown together in a hurry, the language in which people express contracts, and that led to all kinds of problems, including security problems. And then last on the list, it's a possibility, but it's very unlikely, is cryptographic weaknesses. If somebody found some weakness in a hash function or a signing function, that would make your entire currency weak. But typically those sorts of things are very rare because they're checked very, very carefully. There's usually lots of warning ahead of time, plenty of time to actually change your software, change your algorithms before it gets to that point. So those are some of the security issues that can happen with a blockchain, and all things that you need to be thinking about and how you're going to deal with. So what are some of the best practices for the development part of creating the blockchain software in the first place? Well, one of the things that I strongly advocate is using some formal analysis up front. You'll find that every blockchain publishes something called a white paper at the beginning, which is where they lay out their technology, they lay out their algorithms, and they publish this in an academic form so that it can be inspected by peers, particularly people in the academic field, who can give a very thorough review of all of the ideas that are going to underlie the blockchain before you even start beginning to code it. And there are people who are experts in this field, experts in distributed systems, experts in cryptography. Those are the kind of people that you want to be looking at that. And you need to have somebody who, when you're designing the algorithms in the first place, who can actually write a proper academic paper so that it can be reviewed. You need to do a lot of analysis of algorithmic correctness. So if you decide on a new consensus algorithm, say, you need to have that very thoroughly reviewed, that there are no loopholes, no strange race conditions that could happen, ways that it could get broken or out of sync or anything else. And you need to do that analysis at the conceptual level before you start to try to write the code. Cryptographic correctness as well. You need to make sure that you've analyzed all the crypto functions that you're going to use and how you use them to make sure that that's all being done properly. If you're going to use a smart contract language, you need to make sure that your language has been analyzed properly from a programming language theoretic point of view to make sure that it's robust. So that's stuff that you would do all before ever starting to write any code. Now, ultimately, when you write code, you're going to be using a programming language for that. So although I don't want to talk specifically about a choice of programming language yet, because there's other things I want to talk about first, I want to just divide programming languages into some broad families so that we're on the same page about that. So the categories that I like to use are to talk about dynamic languages, and examples of those would be Python and Ruby, where they're very flexible at runtime and most decisions are postponed to runtime. So for example, with a language like Python, if you try to add an integer to a string, it won't detect that until runtime when it actually sees the values that are involved. And if you have a language like JavaScript, it goes even further and it says, hey, you want to add a number to a string? That's great. I'll just convert the number to a string and then concatenate the strings. that's highly dynamic. Then at the other end of the scale, you have what I've called static languages, which would be languages like C++ and Rust and Haskell, where a lot of things are done at compile time, and where instead of being very loose at runtime, nearly everything is already decided by the time the program is built. It's typically built into machine code rather than some sort of bytecode or interpreted language. The weight is all placed at compile time rather than at runtime. And then there's a category of languages that I think fit in the middle that I call managed languages, which would be languages like Java and C#, where there is a lot more going on at compile time, but there's still a lot of things that are done at runtime as well. So they're kind of a hybrid in the middle. And we'll talk more about this as we go through some of the other best practices, but I at least wanted to have some labels there that we would all be able to agree on. So following on from formal analysis at the beginning, before you start coding, what I think is really, really important is emphasizing compile time correctness. You need to be very, very confident that your blockchain software operates correctly. And so the more errors that you can find at compile time before you ever release the software, or even before you start doing unit testing, the more you can do at compile time, the better, because that gives you an absolute guarantee of correctness. So one of the most obvious things that most of us are aware of is the need for memory safety, where it's not possible to end up referring to memory incorrectly and having the program crash or get corrupted. And this is why languages like Python and Java have been preferred over C++ for many years, because with C++ it's possible to have pointer errors and things can get exploited or the software can crash. Whereas those kind of vulnerabilities simply don't exist in a language like Python or Java because it's not possible to make those kind of mistakes. However, it's worth being aware that many of today's cryptocurrencies are written in C++, mainly to achieve performance, and also because a lot of the crypto libraries are written in C or C++. But if you do use C or C++, you are trading performance for safety. Because there are, I mean, C++ is a whole lot better than C, but even then it is still possible to shoot yourself in the foot. But beyond memory safety, something that's starting to be emphasized in the computer industry is the avoidance of null values. So what I mean by that is that in Java, for example, and also in Python, if you have reference to a particular value, in Java, you would be referring to an object, but all object references can also be null, which means it doesn't point to anything. And then if you, for example, try to call a method on that object, well, it isn't an object, and then you get a crash at runtime. And it's very hard to completely eliminate these when you write the code. And so many times when I've been using Java or C# software, all of a sudden it crashes, null pointer exception, and boom, the software's gone, crashed. You have to restart it. You really don't want something like that for blockchain software. However, in those languages, it's impossible to ever ensure that a value can't be null. You have to always put in a check for it. And if the programmer forgets to put in the check, then you have a weakness. Now, there are some languages which have actually dealt with this problem. There's a British computer scientist called Tony Hoare, who actually was involved in the design of Algol 60 back in the day, from which many of our computer languages descend today. Tony Hoare introduced this idea of the possibility of null values, and he calls it a billion-dollar mistake. I actually suspect that by nowadays it's probably $1 trillion mistake. So much waste has happened as a result of this possibility, which seemed like a good idea at the time. But some programming languages have come along and actually designed the language in such a way that there are no null values, which makes that mistake impossible. Now, obviously, for some computations, you do have to be able to represent the possible failure of a result, that a value can not succeed, but you don't necessarily want to throw an exception because it might be looking up a value in a table, for example. And so what Haskell has done, and several other languages like Rust is to provide a specific data type for that. And Haskell, for example, calls it maybe. And a maybe value can be nothing, which is equivalent to null, or it can be just and then an actual real value. But because that's encapsulated in the data type, you have to use that value in a way that reflects the fact that it could be nothing. And the compiler will check that for you, so it makes it impossible to ever check for the nothing value. So Haskell and Rust have this and make very extensive use of it. It does exist in other languages which have something that's often called option or optional, but the trouble is those are optional and you're not required to use them. So it's not as much built into the language as it would be with Haskell and Rust. So I think null values is an extremely important thing to take into consideration when you want to write really correct software. The other thing is strong data typing, and languages vary in the amount of data typing that they have, how strong it is. So Python and Ruby traditionally have had no data typing whatsoever. It's all checked at runtime, which means you don't find out till the software's running that there's a problem. More recently, things have been added to Python, for example, to allow you to have typed annotations on functions, which does improve things quite a bit, but there's no requirement that all functions have type annotations, and it's nowhere near as good as a language that has strong data typing designed into it from the beginning. TypeScript for JavaScript, for example, is a layer on top of JavaScript that adds data typing, but there again, it's easy to escape into untyped JavaScript code, so it's a little bit like shutting the stable door after the horse is bolted. Whereas Haskell, for example, has extremely strong data typing. It's the strongest data typing I've ever seen in a programming language. A lot of people find it frustrating because it gets in your way some of the time, but it does mean that when your code compiles, it nearly always is correct. Static code analysis, which is essentially an extension of the idea of strong data typing, checking as many things as possible before the software runs. Sometimes it's built into the compiler. Sometimes it's a separate tool that you run. So in the case of Rust, for example, it has a thing called a borrow checker, which always makes sure that you're passing memory around correctly. Haskell has a thing called exhaustive pattern matching, where if you have a case statement or a switch statement that checks a number of possibilities, it has a way of ensuring that you haven't forgotten to include any of the possibilities, and it will emit a warning if you have. Linting is something that people are familiar with. There are all sorts of linting tools for every language that check that you followed best practices and there's no things that you may have forgotten about. And we strongly encourage running linting as a part of the continuous integration process. We also strongly encourage turning on all compiler warnings before you actually commit any code to the repository. Immutability is a feature of Haskell and Rust, and typically with functional languages where once you've assigned a value to a variable, you can't actually change the variable. You can only create a new variable that's based on the previous one. And this is an extremely good tool for ensuring that your code is correct and being able to reason about what's actually going on in the program. And as I've said, Haskell and Rust have this, and some other languages do as well. Higher order functions is something that I won't go into very much, but it's where you have functions that take other functions as arguments. And typically these are used to implement things like sorting or loops. And the advantage is that they eliminate what are called off by one errors, where you have a loop, but you don't have the beginning or the end of the loop. Either it accesses too many things or too few things, whereas if you use a higher order function, it automatically ensures that the loop is correct. And another thing that's really valuable to have is something called software transactional memory, which is a way of dealing with race conditions. And one of the problems with race conditions that I talked about earlier is that if you say, oh, well, I'll just throw a mutex on that, you can actually end up getting deadlocks if different parts of the code lock the mutexes in different order. What software transactional memory is a way of essentially locking everything as a bunch, similar to a transaction in a database where either the whole thing succeeds or the whole thing fails. And if at any point it gets to a failure, instead of blocking, it actually aborts and you have to go back and retry the transaction. Now, there are libraries for doing this in lots of languages, but some languages have it much more built in than others. And one of the things I like about Haskell is it has a really good STM implementation that makes it very easy to make use of. It's a very powerful technique. So all of that is a form of compile time correctness. So just going back to the idea of a choice of programming language, when it comes down to this, what you need is a language that's both safe and fast. Obviously, you want it to be safe so that it doesn't crash or make mistakes at runtime, but you do need it to be fast as well because of this runtime requirement of high throughput and having to share resources. And there are not many languages around that are both safe and fast. You've got C++ that's fast, but not 100% safe. And then you've got languages like Python and JavaScript, which are safe or safer, but not at all fast. So what we feel at FP Complete is that Haskell and Rust hit the current sweet spot among programming languages for languages that are both safe and fast. Rust's speed is on a par with C++. It's maybe not quite as safe as Haskell, but pretty close. Haskell is definitely top of the game in terms of safety and correctness. Its performance is usually within a factor of 2 of C++. And if you work hard to optimize your inner loops and your key algorithms, then you can usually get it to within a few % of C++. So we think that Haskell is a really good choice for a lot of things too. And for those of you who are familiar with our company, you'll know that we have tended to specialize in Haskell over the years, but we have added Rust recently. Okay, another best practice that you can use in your blockchain development is what we call property-based testing. So many of you will be familiar with the concept of unit testing, and property-based testing is technically a form of unit testing, but what you may think of as unit testing is what we call example-based testing, where you create a unit test and you have some fixed inputs and outputs, and then you run the function to make sure that given those inputs, it produces those outputs. But the trouble with that is it's only as good as the number of test cases that you write, and it's very hard to write a really comprehensive set of test cases that cover all the possibilities. So property-based testing takes a different approach. Instead of using examples, what you do is you assert properties that must be true of your function's outputs. Basically, you're asserting what makes the function's output valid. So to take a very simple example, if it was a sort function, for example, you could assert that the first element of the output list has to be greater than all the others in the list, or smaller, depending on which order you're sorting in. That would be a property that you could assert about what makes the output valid. So what you do is you create a range of properties that have to be true of the output. And then what you do is you run the function with a large number of randomly generated inputs, and you check that the properties are always true of the outputs. And the advantage of this kind of testing is that it's really good at finding edge cases that you wouldn't have thought of. Especially if a programmer writes their own tests, typically they won't write a test for the edge cases that they've forgotten to implement, because the whole point is that they've forgotten that that was a possible edge case. Property-based testing is great because it will find all kinds of things that you wouldn't have thought of in terms of empty lists and strange combinations of things. So it allows you to take your code to a higher level of correctness than you would have been able to do previously with just example-based testing. There's still a place for the example-based testing as well, so really good software will use a mixture of both. But you're able to use frameworks for the property-based testing so that the random generation of the inputs and the checking of the properties and so on is all done automatically. The other thing that the property-based testing frameworks do nicely is what's called shrinking, which is that if you have some large randomly generated input and it fails, well, you've got a big problem trying to figure out where the problem comes from. But the framework will actually shrink the test case down until it gets a minimum set of input values that will generate the problem, and then that's what it presents to you. And the goal here is to achieve what are called total functions in the functional programming world, which is a function that has an output for every possible input. It doesn't just simply crash when it gets certain inputs or produce undefined values. So property-based testing will enable you to check that all of your functions are total, that they produce an output for every input. Now, the output may be something like throwing an exception or returning a nothing value, but nevertheless, it is code that operates to specification for every possible input. And this is the kind of thing you really want for something like a blockchain, because it's so hard to test a blockchain adequately in the lab unless you run thousands of nodes with a huge throughput, because you just simply can't foresee all of the strange things that could happen in the world. Now we have a blog post on property-based testing that's really very well done, written by a colleague of mine called Sid. I highly encourage you go and look at that if you don't know anything about property-based testing, and there will be a link to that at the end of the presentation. Okay, moving on with best practices. Effective use of CI/CD. So CI stands for continuous integration, CD stands for continuous delivery or continuous deployment. So continuous integration means that if your software is composed of various parts, then you automatically integrate them together and build them together and run the tests on them, usually on some sort of server that's dedicated to managing that. And continuous delivery means that as you make new commits to the trunk in the repository or to master, that software gets built and then automatically deployed to an environment, typically to a testing environment that reflects the production environment pretty closely. So most companies are doing some sort of CI and maybe some CD, but in our experience as a consulting company, we found that the majority of companies are not making as good use of the CI as they could do. So you definitely want to do as much checking as possible in CI. You don't just want to build the software and maybe throw a few automated unit tests at it. You want to be doing as many different kinds of tests as you can actually possibly do. So basic things like making sure that all warnings are enabled when you do your builds, making all warnings errors so that it's not possible to have a successful CI build unless there are no warnings. Often I build open source software or libraries, and I'm disappointed to see how many uncorrected warnings there are. And for really production quality software, there shouldn't be any warnings. Linting, I've already talked about. You should be running your linters in CI, and it should be a CI failure if the linting produces any warnings. The great advantage of CI is that it's a clean environment for building and testing. So you don't get into this works on my machine situation that can happen. You're always starting with a known environment, both for your build and for your test. You're just aiming to validate everything you can think of, validate that it's true of what you're building, and automated everything. Often companies have integration tests, but they're not automated. So we encourage you to automate all of your integration tests and your full system tests and everything else, and actually trigger those from your CI builds. Maybe manually, but certainly have it so that they can be run in CI. So there's never an excuse of, oh, I didn't have time to do that, or I forgot to do that. So integration tests, and it is even possible to do infrastructure tests through CI, to actually have CI jobs that will actually go out and probe your infrastructure and verify that various properties of your infrastructure are true. That can be a very effective technique. Other things that you want to do in CI/CD, use staging environments. Most companies are doing this already. You'll have a dev environment, a QA environment, or a test environment, and a production environment, which are all set up to be pretty similar, so that people can test the software before it goes live, but in a form that's as similar as possible to how it will be deployed. What you do want to do, if you possibly can, is to build your branches before they're merged. So if somebody works on a feature, puts it on a branch and has it reviewed, you want to make sure that your CI software builds that branch before you ever think about reviewing it or merging it. And that will catch so many things, so that by the time that feature is merged to master, you already know that it passes all its tests and everything else. But if you don't have a CI setup that can build any given branch, you're kind of running blind. You don't find out until stuff's merged to master that the tests got broken or whatever else. And what you ideally want to do is not just build it and run the automated tests. What you want to do is actually deploy it to an environment and have somebody try it out there. And this is a concept called review apps, where you can basically create and tear down temporary environments that match your typical dev environment, where you can deploy what was built from just that branch to that environment and then have somebody go try it out, see how it looks. We're big fans of the GitLab CI system, and review apps is a really neat feature that GitLab has. Another thing that you want to be doing is matrix builds. Some of you may be familiar with this term. That means that when you build, you're building for all combinations of build options, and that's why it's called a matrix. You have sort of rows and columns that represent settings for options. You want to be building all of those every time, so that you know immediately about failure with some particular combination of build options, whether it's for a particular operating system and platform, or some other option that you build with, some compatibility option or anything else. So you should be having matrix builds rather than just building for the common case, which would say just be, you know, building for Linux in debug mode or something like that. The other thing we emphasize strongly is to use the artifacts. So when you do a CI build, it will end up with various binaries and so on that it's built, and those should be archived by your CI system, and then it should be possible for people to get at those artifacts through some URL and be able to download them and use them, run them, and do things with them. What we do strongly encourage is building Docker images, because that bundles up not just your executable, but also all of its dependencies and other things that it needs at runtime. So it gives you a very repeatable package, capsule, that you can then run, and you will know that if that Docker image runs correctly in one place, it'll run pretty much anywhere else. And there isn't this issue of, oh, well, we forgot to install this dependency. We think best practice is to not just build Docker images, but to actually upload them to a registry, typically a per project registry, so that people can then just Docker pull to run them. That removes a lot of the friction in using them. Again, GitLab has a really nice facility of a per project Docker registry. You don't have to do anything to set that up. You get that automatically if you just tick the box. And that means that people can easily just pull down the latest image from CI and test it and use it. We also encourage using CI artifacts as the source of truth. One of the things about software builds, and that includes Docker builds, is if you build it tomorrow, you may not get an identical result to if you build it today, for various reasons, because dependencies may have changed or other things, and you can only control those so much. So what we encourage you to do is to automatically build in CI all the artifacts you're going to need every time a new commit is made. And then anytime you want to build from that commit, you use the artifacts that come from CI as the source of truth, so that you know that everybody is using an identical binary corresponding to a given commit. Another technique that's very helpful that goes along with this is called pinning, where with all of your dependencies, you fix them at a particular version. And that includes not just the libraries you may use that other people have produced, but actually within your own project. Ideally, different parts of a project will be pinning the versions of other parts of the project that they're building against, and then the versions get upgraded in a controlled way. This can be quite a powerful technique, and ideally what you want to have is that if a developer is working on a particular subsystem, he doesn't have to build binaries for all the other subsystems as well. He will get them from the CI artifacts from the other subsystems, and everybody's using the same thing, and they shouldn't even have to figure out how to build something that they're not working with and debugging all the time. Okay, best practices, continuing. Auditing is a really important thing. I think you probably would be required to do that for a lot of blockchains. So what you do want to do is to have third-party auditing of your application code, somebody from outside looking at that and doing a thorough report on it. But you also want to be doing auditing of your dependencies, all the libraries that you depend on, whether there are vulnerabilities with them or vulnerabilities that can happen if you don't use the right practices surrounding them. And you need to have a third party doing this. Typically, auditing is actually a requirement, for example, if you want your cryptocurrency listed on an exchange. But it's a really good best practice technique to do, to not just have your own developers review things, but to actually have an outside agency come along and do that. Open source. You can use open source as a consumer. You can basically use open source libraries. Definitely make use of open source. There's so much good stuff out there. Contribute to it. If you're using libraries, then as much as possible, try to contribute to them, not just as a payback, but also because then you can get the features that you want and get it to move in the direction that you want it to go. But you do need to know how to interact well with an open source community that surrounds a particular project, just what the etiquette is. But you can also be a producer of open source, particularly for a blockchain. Making your software open source is a huge benefit. It creates trust among all of the people who are going to be using the blockchain because they can see what went into making it up. It increases security because, as I'm sure many of you have heard, there's the many eyes philosophy, that the more people you have looking at your source code, the more likely vulnerabilities are to be found ahead of time before it becomes a serious problem in production, before you can deal with it. And often people who spot vulnerabilities will contact you privately and give you 90 days or something to be able to fix it before releasing the information to the public. So you have 90 days to rebuild the software so that hopefully your software is already fixed before anybody starts trying to exploit it. You didn't have the many eyes approach. If it's just closed source software, you often don't know about vulnerabilities until somebody finds it in the software that's already deployed, and then it's too late to do anything about it. Well, not too late, but then you're scrambling to keep up. And another thing about making your software open source is it allows reuse and integration of whatever you produce. People can build things on top of it, integrate it with other services that they're providing. And what you're doing thereby is making basically an ecosystem surrounding your blockchain that other people want to get involved with, and that will really drive adoption. Okay, what kind of things might a company need help with if they were going to implement a blockchain? So the lowest level of help would be what's called augmentation, where basically an outside agency comes along and augments your team in some way. So the simplest form of that would just be training, where they come in, train all your people, and then get out. So there could be training in programming. Also training in DevOps is very valuable. We found that knowledge of best practices in DevOps is sadly lacking these days. So with training, the company would come in and then leave. But mentoring would be more of an ongoing relationship where that sort of training continues, and it's more done on a case-by-case basis of whatever people are working on. Partnership would be the next level up, where there would be a mixture of engineers on the team. Some are from the outside agency, some are from your internal engineers. So you might, for example, want team leadership provided by an outside agency, but with your own developers doing most of the coding. You might want help with designing the system architecture in the first place, designing some operational best practices right at the beginning of the project for things like intrusion detection and response planning. You might want to have somebody outside set up some of your DevOps for you that then your own people can continue to maintain, help with optimization if the software's not running fast enough, help with debugging difficult problems, or perhaps just writing some component of functionality that you need as a library that you link to if it requires some sort of specialist expertise. You may well want help of reviewing your software, not so much the auditing, but just the reviewing as things go along. And then, as I've mentioned, the auditing, which is something that would happen towards the end and would also be required by cryptocurrency exchanges. Beyond that, an outside agency could have direct responsibility. They could do, for example, the initial implementation up to a 1.0, or they could do ongoing development after that as well, taking it up to 2.0, 3.0, and so on. Or you could just have your own engineers take over after 1.0, and especially if there's a partnership relationship, hopefully they would know enough about it at that stage to take it from there. Even beyond that, there's maintenance, which is fixing problems or slowdowns. You can do that yourselves or have somebody outside do that. Operations, actually running all the cloud nodes that form the backbone of the network, you can actually contract that out to somebody else. So what issues need to be decided before proceeding with your blockchain project? And we're getting close to the end here. Well, first you need to decide what are your requirements. Could you build on top of an existing blockchain rather than implementing your own? That is sometimes a possibility if it meets your needs, but you need to decide what you actually require. Do you have any unusual needs or ideas that you need to see in this blockchain? Some sort of unusual consensus algorithm, for example, which the Genie Foundation had, or do you need a higher level of anonymity and privacy in your blockchain? There are some techniques. Homomorphic encryption is one of them, which is a pretty cool thing. I encourage you to look that up. And also Tor, which is a way of anonymizing your IP address. Or some sort of extreme decentralization that you need. If you have requirements in that area, you probably need some outside help. Should you engage a crypto consultant? Unless you're using absolutely vanilla crypto technology, it's always good to get an expert involved who can advise you on some of that stuff. But you need to decide whether what you're trying to do merits that kind of help. Then, of course, you have to decide what software technology you'll use, choice of programming language. Even though most of them are done in C++, and then probably the next most common one is Haskell, there are people using all sorts of different programming languages. Some are in Java. I think possibly some might even be done in JavaScript with Node.js. I'm not sure. What platforms are you going to target? Are you just going to hit Windows and Mac OS? You're going to do Linux as well. You're going to do stuff with mobile. What framework will you use for the UI? Will you have one of the traditional desktop frameworks like Qt, or would you want something where you can use web technologies and use a tool like Electron that allows you to have a bundled app that has a web technology-based front end? And what are you going to do about mobile support? Most mobile devices don't have the horsepower to run a full blockchain, but there are ways of allowing people to have access from a mobile device. What cloud provider will you use? There are a lot to choose from. There's Amazon, there's Google, there's Microsoft, and so on, or maybe one of the smaller ones. How are you going to implement high availability? Obviously, you're not in control of the availability of end users' nodes, but if you're running a bunch of them in the cloud that are doing a lot of the heavy lifting, how are you going to make sure that those have high availability? What are you going to do about secrets management? You know, it's not enough just to store them on some engineer's machine. Those secrets need to be shared in a disciplined way, and there are software tools around for doing that, but which one are you going to use? They have different pros and cons. So you will have to ask yourself, how much in-house expertise do you have? Do your existing engineers have the expertise that they need to be able to carry this project right through to completion? In the area of cryptography, in the area of distributed algorithms, in the area of DevOps best practices, open source best practices. Do you have all of that expertise in-house? Because if you don't, you've either got to grow it or get outside help, or a combination. The bottom line is that having thought about all of those things, you need to decide how much additional expertise do you want to develop in-house, how much external help will you need, and ultimately, who will you go to for that help? What companies are around that have expertise with blockchain and cryptography and other things that would be a really solid resource for you to lean on? Okay, so over to you, Greg.
Thank you, Neil, for a very thorough presentation and discussion into blockchain development use case scenarios. For those of you here today for educational perspectives, thanks for your support. Please feel free to continue to attend, learn from, and support FP Complete with its many blogs and webinars. As this slide, as you can see this slide, I need to mention that over the past few years, we've been immersed in blockchain and cryptocurrency conventions. And one major thing I've learned is every corporation, every organization needs somebody like FP Complete. And why, you ask? Well, I recently met somebody at the KubeCon in San Diego, and when I walked up to the CEO, he was literally floating in his chair, and he looked very relaxed, and I addressed that immediately. And I asked him, how are you so relaxed? And he said, look, the relationship with FP Complete's engineers is incredible. He said we never get stuck. We save time and money. He said we directly lessened their technical debt and their cultural debt. And he even smiled at me after and said, you make my family life better. So as this slide states, we're engineers to engineers. We ask the right questions to keep your project on track. Little humor, but very true, a lot of truth in this. It's gold for nerds. Some of the products we have experience with that are mostly directed towards DevOps, but like HashiCorp and so forth are something that we have experience within blockchain.
And as you said, Greg, good DevOps is a really big part of doing a blockchain well.
Absolutely. Some of our roles, as mentioned earlier, blockchain development, blockchain audits, blockchain consulting. We have many years hands-on experience within these roles. Some references for those of you that have attended.
So I think probably one of those is the blog that I mentioned on property-based testing, somewhere in there.
Other success programs FP Complete offers, including the blockchain success programs. For those of you that are here to utilize FP Complete for its blockchain or any other services, or if you'd like to continue upon or ask other questions, please contact us online at fpcomplete.com/contact us. Or if you prefer to speak with a human, call us at 858-333-6397. And we will grab Neil or another one of our best blockchain engineers to begin discussions on your pain points and how to move forward with the project with FP Complete. At this point, I see there is a couple questions from the panel. One of them is, how can an organization switch its language of choice? And does this require us to start over per se?
Yeah, that's a good question. Obviously, switching programming language is a big thing. I think it partly depends on how different the programming languages in question are. So if you were switching from, Python to Haskell, that would be a huge change, and you definitely need some outside help to train your engineers to think differently about how programming is done. If you were switching from, say, Java to C#, I think that would be a fairly manageable step, and probably a lot of programmers would be able to train themselves in that. It depends on also what cross-language interoperation facilities there are. It may be possible to keep some of the code that you've written in your existing language as libraries and use that from whatever new programming language you want to work in, and then gradually over time migrate the code over to the new programming language. Particularly if you work in the Microsoft.NET family of languages, for example, there's very good interoperation across the different languages. Haskell has a very good story for using external functionality in C and C++. So very often the crypto libraries that we would be using would be written in C and would be very high performance, but then they can be accessed in a really natural way from Haskell. And the same is true with some other languages.
Okay, and I also see, is there specific preparation or an organization should perform previous to reaching out for an outside consulting service?
Yeah, that's interesting. I think it's really helpful to have a thorough inventory of all that you're doing internally. For example, the different CI systems that you're using. What is the collection of engineers that you have? What skills do they have that maybe they aren't using every day? How is your DevOps run? You really want to do take the pulse of all of those, do a health check. although one of the services that we offer is actually to do a DevOps health checkup, where we can come in and review all that you're doing in the DevOps field and then produce a report at the end of that, kind of an audit. But it really helps if you've investigated quite a few of those things yourself and identified what are our pain points, what are we failing at that we could be doing better? And then if you can come to an outside agency with a list of those things, these are the specific areas that we need help with, this is what works well, this is what's broken, that initial conversation is going to go much better.
Well, great. Once again, thanks to Neil Mayhew, and this is Greg Moranci, the Marketing Director from FP Complete. I want to thank everybody for attending today's webinar, and please feel free to reach out, and everybody have a nice day.
Thanks, everybody. Bye.